Hey everyone, welcome back. Before we embark on today's truly monumental topic, I'm sending out a massive wave of positive energy and the very best wishes to all of you watching. Seriously, wherever you are in the world, I genuinely hope you're feeling fantastic, taking excellent care of yourselves, and staying healthy. That's the bedrock of everything good in life. Now, get ready to shift your perspective on some of Earth's most majestic features. We often look at towering mountain ranges like the Himalayas, the Andes, or the Alps and think of them as ancient, permanent, unchanging monuments. They feel solid, eternal, like they've always been there and always will be. But here's the incredible, ground-shaking truth. Mountains aren't static. They can actually grow taller, right before our eyes, driven by the immense, slow-motion forces deep within our planet. That's right. Those colossal peaks scraping the sky are actively rising, pushed upwards in a geological drama unfolding over millions of years, yet measurable even within our own lifetimes. The Himalayas, home to Mount Everest, are the ultimate poster child for this ongoing growth spurt, a direct result of the relentless dance of tectonic plates. It's a powerful reminder that our planet is a dynamic, ever-changing stage, even on the grandest scales. So, how does this mountain building magic work? Forget instant creation. This is a process measured in millimeters per year, but compounded over vast stretches of time. It creates the most spectacular landscapes on Earth. The key players are Earth's tectonic plates. Imagine the Earth's outermost shell, the crust, and the very top part of the mantle isn't one solid piece. Instead, it's broken into about a dozen giant, rigid slabs, like pieces of a cracked eggshell floating on a layer of hot, slowly flowing rock below, the asthenosphere. These plates are constantly on the move, driven by the intense heat radiating from Earth's core, which causes the mantle rock to convect, rise, cool, sink in massive, slow cycles. This convection acts like a giant, incredibly sluggish conveyor belt, dragging the plates along with it. Plates can move apart, divergent boundaries, slide past each other, transform boundaries, or, crucially for mountain building, crash together, convergent boundaries. When plates collide, it's like the ultimate slow-motion car crash on a planetary scale, and that's where mountains are born. The Himalayas offer the most spectacular example of this continental collision. Picture Earth roughly 50 million years ago. What we now know as the Indian subcontinent wasn't connected to Asia. It was a massive island continent, adrift in the ancient Tethys Ocean, and it was on a collision course. Driven by the churning mantle below, the Indian plate was racing northwards at what, in geological terms, was breakneck speed, maybe 15 centimeters, 6 inches, per year. Ahead of it lay the much larger Eurasian plate. There was no stopping it. Eventually, the leading edge of the Indian plate slammed into the southern edge of the Eurasian plate. But continents aren't like thin, dense oceanic crust, which usually just dives, subducts, beneath another plate. Continental crust is thicker, lighter, and more buoyant. Imagine trying to push two thick blocks of styrofoam together underwater. They resist sinking and instead crumple and buckle upwards. That's essentially what happened. When India hit Asia, neither plate wanted to dive deep into the mantle. Instead, the immense force of the collision caused the rocks at the leading edges to crumple, fold, fracture, and pile up on top of each other. It was the ultimate geological pileup. This crumpling and piling created a massive, tangled knot of rock, the initial, primordial Himalayas. But the collision didn't stop. The Indian plate is still pushing northwards into Asia today, though at a slower pace of about 5 centimeters, 2 inches, per year. Think of India as a gigantic, unstoppable bulldozer ramming into southern Asia. This relentless pressure means the crumpling and thickening of the crust is ongoing. Rocks are forced upwards along massive cracks in the earth called faults. Huge slabs of rock, kilometers thick and hundreds of kilometers long, are thrust upwards and over other rocks. This process, called thrust faulting, is like one layer of the crust being peeled back and stacked on top, dramatically increasing the thickness and height of the crust in the collision zone. It's not just gentle uplift, it's a violent crumpling happening incredibly slowly. The immense pressure also causes rocks deep down to heat up and change form, metamorphism, creating new minerals, and sometimes even melting to form magma that rises and cools into granite batholiths, adding further bulk deep within the growing mountain root. This brings us to a crucial concept, isostasy. Imagine the Earth's crust floating on the denser, more fluid mantle below, much like an iceberg floats on water. The floating crust seeks gravitational balance. When you pile a huge amount of rock on top to form a mountain range, you're making that section of crust much thicker and heavier. However, the thick crust also extends deep down into the mantle, forming a root, much like the bulk of an iceberg is underwater. This root is made of lighter continental crust material displacing denser mantle rock. Because the mountain has this deep root of lighter rock, the whole system stays balanced. But here's the key point. When the collision forces pile even more rock on top, making the mountains taller, the crust gets thicker and the root gets deeper. This temporarily upsets the balance. The thickened area sinks deeper into the mantle to compensate for the extra weight on top. However, the process of sinking also generates upward pressure along the edges of the sinking block. Think of pressing down on a thick sponge in water. The part you press down sinks, but the sides bulge upwards. Similarly, as the massive Himalayan block sinks deeper into the mantle under its own growing weight, a process called isostatic adjustment, it also pushes the peaks themselves even higher. It's a complex feedback loop. Collision forces push rocks up. The weight of the mountains makes the crust sink deeper. The sinking squeezes material upwards at the edges, further raising the peaks. This isostatic rebound is a significant contributor to the ongoing rise of the Himalayas, even as the main tectonic shove continues. Now, you might be thinking, okay, it's moving centimeters per year. How can we possibly know the Himalayas are growing right now? We have amazing technology that gives us a real-time view of this geological drama. The most direct evidence comes from GPS, Global Positioning System. Scientists have installed incredibly precise GPS receivers all over the Himalayas, including near the summit of Mount Everest. These instruments don't rely on the maps on your phone. They use signals from satellites to measure their position on Earth's surface down to the millimeter level, continuously, year after year. What these measurements clearly show is that stations in southern Tibet and on the peaks of the Himalayas are steadily moving northwards and upwards relative to stations on the stable interior of Asia. The northward movement confirms the Indian plate is still pushing into Asia. The upward movement? That's the mountains actively rising. Measurements show that parts of the Himalayas are uplifting at rates of about 1 centimeter per year, or even more in some spots. While 1 centimeter might seem tiny, remember, that's every single year. Over a decade, that's 10 centimeters. Over a century, it's a meter. Over the millions of years the collision has been happening, those millimeters and centimeters add up to kilometers of uplift. We can also see the strain building up in the rocks through seismology, the study of earthquakes. The ongoing collision builds up immense stress along the major faults. When that stress exceeds the strength of the rocks, it's released suddenly as an earthquake. These earthquakes, some devastatingly large, are literally the mountains growing in painful, jerky increments as rocks shift and move upwards along faults. For instance, the massive 2015 Gorkha earthquake in Nepal involved a section of crust lurching upwards by several meters in just seconds, a dramatic, violent leap in the mountain building process. Even more recently, studies of a 2020 earthquake near Dzungaria showed significant crustal thickening and uplift related to the ongoing India-Asia collision. But hold on, if the mountains are constantly being pushed up, why aren't they infinitely tall? Why doesn't Everest just keep shooting into space? Because there are powerful forces working against the tectonic push, constantly wearing the mountains down, erosion. Think of mountain growth as a giant, slow-motion tug-of-war. On one side, you have the immense tectonic forces generated by the colliding plates and isostatic adjustments, relentlessly pushing the crust upwards. On the other side, you have the destructive power of water, ice, wind, and gravity, constantly breaking down the rock and carrying it away. Glaciers are like colossal icy bulldozers, grinding away at the peaks and carving deep valleys. Rivers, fed by rain and glacial melt, are nature's power washers, cutting deep gorges and carrying countless tons of sediment down to the oceans. Freeze-thaw cycles crack rocks apart. Landslides send huge chunks of mountainside tumbling down. This erosion is incredibly efficient. In fact, scientists estimate that without the ongoing tectonic push, erosion would wear down a major mountain range like the Himalayas to relatively low hills in just a few million years. The majestic height of the Himalayas is a direct testament to the fact that the rate of tectonic uplift is currently winning the tug-of-war against the rate of erosion. For Everest, it's estimated that tectonic forces push it up by about 1 centimeter per year, while erosion wears it down by about 0.3 centimeters per year. So it's still gaining height, just more slowly than the pure uplift rate suggests. The sediment washed into rivers like the Ganges and Brahmaputra, forming the vast delta in Bangladesh, is literally the ground-up remains of the Himalayas being carried away. The growth of mountains like the Himalayas is far more than just a fascinating geological process. It has profound effects on our entire planet. Firstly, it dramatically alters global and regional climate. Towering mountain ranges act as massive barriers to atmospheric circulation. They force moisture-laden winds to rise, cool, and drop their rain or snow on one side, the windward side, creating lush environments, while leaving the other side, the leeward side, in a rain shadow, often arid or desert-like. The rise of the Himalayas is thought to have played a key role in intensifying the Asian monsoon system. Secondly, the process of mountain building creates an incredible diversity of mineral resources and unique geological formations exposed by the uplift and erosion. Thirdly, and crucially, it drives biodiversity. As mountains rise, they create new habitats with varying climates, from tropical foothills to icy peaks, over very short distances. This isolates populations and creates opportunities for new species to evolve, making mountain ranges like the Himalayas global hotspots of unique plants and animals found nowhere else. The ongoing uplift continues to create new ecological niches. Moreover, the weathering of rocks in these vast, growing mountains plays a role in the long-term carbon cycle. Minerals exposed to rain and air absorb carbon dioxide, helping regulate Earth's climate over geological timescales. So, the next time you see a picture of the Himalayas or any great mountain range, see them not as frozen monuments to a distant past, but as living, breathing entities in a state of dynamic flux. They are the dramatic scars of a titanic, ongoing collision, a slow-motion battle between continents. They are actively rising, millimeter by painstaking millimeter, year after year, propelled by the relentless drift of tectonic plates and the isostatic adjustments deep within the Earth. We can now measure this growth in real time using satellites and GPS, witnessing geology in action. Yet, simultaneously, they are under constant siege by the forces of erosion, water, ice, and gravity, tirelessly working to grind them back down. Their majestic height is the current balance point in this epic struggle. They shape our climate, our resources, our ecosystems, and even the chemistry of our atmosphere and oceans. Mountains like the Himalayas are the most visible testament to the incredible, restless energy contained within our planet, constantly reshaping its surface over millions of years. They remind us that Earth is a dynamic system, where even the mightiest peaks are just temporary features in an endless cycle of construction and destruction, born from fire and force, reaching for the sky even as the elements try to pull them back down. It's a humbling perspective on scale, time, and the powerful forces that forged and continue to forge the world we live on. Thanks for exploring the rising giants with me today. Stay curious, stay healthy, and keep looking up, way up, in wonder.